Assalamualaikum warahmatullahi wabarakatuh. Hi, good evening. My name is Miqdad bin Fadzilah. My matrix number 210290. My partner is Putra bin Zulkiflee. The matrix number 210016. So we're from group 7. So today we're going to talk about the assignment mathematics from ENG 3002 that given to us around 2 weeks ago. Uh, so let's get started. So for the first assignment is Newton's second law and Archimedes principle. So for the first is introduction. So I write the history of Newton's second law of motion, and then I write the background and biography of Sir Isaac Newton itself. Next, history of Archimedes principle, uh, and then I also write the background and biography of Archimedes, the Greek scientist, and I put some related information with ordinary differential equation (ODE) that related to the Newton's second law of motion and the Archimedes principle itself. So next, for the principle, uh, for Newton's second law, uh, I write in terms of body orientation, average and instantaneous velocity, and the last one is acceleration and object. And then I put some equation that show connection between ODE, ordinary differential equation, and Newton's second law itself. And next principle is Archimedes principle. I explain about the buoyant force itself. That as we know that buoyant force is the vital component in the Archimedes principle right now. So and then I put also I put some uh, equation that shows connection between ODE, ordinary differential equation, and Archimedes principle itself. So I'll pass to Zoharis to talk about application and example for ODE for Newton's second law of motion and Archimedes principle. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Putra bin Zulkiflee. Now I will be presenting about the application of Newton's second law and Archimedes principle. Moving on to the Newton's second Newton's second law of motion. Second law, the application of Newton's second law. First, there are some application that we imply in our daily life, such as pushing a car or any other object. Because, for instance, a car and a drug, by comparing the acceleration produced by a car and a drug with the same amount of the magnitude of force to the vehicle and the drug, the vehicle accelerates faster than the drug because the vehicle have the lower mass than the drug. Other than that, we also can see the application in racing car. By reducing the weight of racing car increase their speed, engineers try to keep their vehicle at a very low mass as low as possible, as a lower mass means more acceleration, and the higher acceleration, the more chances to win. Other than that, we also can see that Newton's second law also be implied in rocket launching. During rocket launching, a force known as thrust is required for a rocket to leave Earth's orbit and enter space. According to the Sir Isaac Newton law of motion, force is proportional to acceleration. The rocket speed allows it to escape the gravitational field on the Earth and enter space. Moreover, we also can notice that there is Newton's second law of motion, Newton's second law of motion in car crash. During the impact of force that occurs between the force between the obstruction and the car during the car during a car accident. The magnitude of the impact force is determined by the mass of items colliding and the speed at which they are moving. This means that the bigger the mass of the items colliding, the greater the intensity impact force will be. Uh, will be. Sorry. This means that the bigger the mass of the items colliding, the greater the intensity of the impact will be. Last but not least is throwing object from a certain height. When we are throwing object from a height, when object is hurled from a given height, when the object being thrown by a certain height, the Earth's gravitational force assists it in accelerating. As the object approaches the Earth, its acceleration increases. Acceleration created by a body that is directly proportional to the force. According to Newton's second law, the impact force is activated when the object collides. The object collides with the ground. That is why a fragile object thrown from a tall structure will distort more than a brittle thing launched from a lesser height. Moving on to the application of Archimedes' principle. On the other hand, Archimedes' principle also has application to human. The first application that I would like to bring up is in a submarine. A submarine has a big ballast tank that helps in maintain its position and depth below the water surface. It's apparent from Archimedes' principle that the change in object mass changes the amount of liquid that must be displaced. Ballast tanks in submarine are in charge of this. The submarine has less mass when the tanks are empty and it floats like a normal ship. When the ballast tank filled with water, the mass increases and will and drown the submarine. Moving on to the next application is in the balloon in the air, hot air balloon. That a balloon will float if it is filled with a gas that is less dense than the air. The air trapped under the canopy of hot air balloon is less than the surrounding air. Hence, the balloon will ascend once again. Moreover, Archimedes' principle also being applied in the hydrometer. A hydrometer is an instrument to measure liquid relative density based on buoyancy. Following one of the biggest application and contribution to the human community is the ship. A ship floats on the sea surface because the amount of water displaced by the ship is sufficient to give it a weight equal to its own. The ship from hollowed out to make the ship's total density smaller than seawater. As a result, the buoyant force is acting on the ship is sufficient to sustain its weight. Density of seawater varies with location. It depends on many factors such as the temperature of the water. When the ships will float higher in cold water than in warm water because the cold water has a larger density. Let's move on to the modeling of the Newton's second law by the application of first order differential equation. So here we can see the modeling the equation here is F plus M dv over dt equals to mg, where F is the force, while M is the mass, and G is acceleration due to the gravity. The examples of the modeling in Archimedes' principle, Newton's second law of motion says summation of F equals to ma. Hence, we can use this idea because we can write equations for the forces acting in the object. The weight of the object is written as rho Al times G. The buoyant force of the liquid can be written as rho Eg, which is mercury, times Y plus YT. That's all for the Archimedes and Newton's second law of motion.
So we move on to the next assignment. This is assignment 2. The title is wave equation. So for the first page is introduction. So I just put some explanation about the wave equation, and then I write the history of the wave equation, and then I put some biography of D. Allenberg, which is the founder of the wave equation itself, and then I explain the terms of partial differential equation (PDE). So my section in the introduction demands a lot of information and comprehension, since I need to be able to connect the partial differential equation and the wave equation itself. So this evidence, when I describe how the partial differential equation plays a critical role in equating the wave equation itself. So next is principle. So the principles we're going to talk about the linear versus nonlinear equation, and then I explain how to solve the nonlinear equation using the PDE, partial uh, differential equation, that show connection from the wave equation itself and PDE itself. So and then the second principle is solving an inhomogeneous wave equation using the Duhamel's principle. So when we talk about the Duhamel's principle, I will explain how to solve an inhomogeneous wave equation using the Duhamel principle, that a lot of equation that related to the wave equation itself. So uh, it's going to more practically and more systematically when the equation itself um, to show to in assignment. So that's all for me. I'll pass again to the Zuharis to talk about the application and example about um, wave equation that related to the partial differential equation. So that's all for me. Thank you.
Assalamualaikum. Okay, now I will be presenting about the application of wave equation. Moving on to the next slide. Okay, wave equation in pile foundation study. The wave equation is commonly used to study pile foundation, bearing capacity, resistance. A geotechnical engineer may advocate a deep foundation over a shallow foundation for a variety of reasons, but some of the more typical ones are very large design loads, poor soil at short depths, or site constraints. There are different terms used to describe different types of deep foundations, including piles, drill shafts, caissons, and piers. Wave mechanics have been employed for the analysis of piles during impact driving for the last 40 years. Moving on to the next slide, wave equation in rod. Consider an elastic rod that has been hammered at one end. An elastic deformation pulse will propagate through the rod as a result of this experiment. The general equation for deformations and stresses in an elastic medium is the starting point for a mathematical model for longitudinal waves along an elastic rod, where rho is the density, u the displacement field, the stress tensor, and F body forces. The latter has normally no impact on elastic waves. Moving on to the example of partial derivative in wave equation, all wave equation solution is written as f in bracket x plus vt, f in bracket x plus vt, and g in bracket x minus vt, g x minus vt are superpositions of left traveling and right traveling waves, while f x plus vt times x in bracket x plus vt and g in bracket x plus minus vt times g x minus vt respectively. While the basic shape of the wave remains constant, the wave translates to the left or right in time, earning its names left traveling and right traveling. Because the equation is linear, any superpositions of solution is so because the equation is linear, any superposition of solution to the wave equation are also solutions. Right, thank you for listening. That's all from us.